Welcome at Eindhoven University of Technology, and we are talking wireless communication. In fact, we are talking about wireless communication via light. We see that we can communicate via LEDs in the ceiling, or we can even modulate lasers and have a beam with a very high bandwidth transmitting high bitrate data. But increasingly, it's not a transmitter, not an emitter, not a laser that is limiting the speed of communication. It is rather a problem of the detector, a problem of the photodiode that is trying to capture enough photons at a high speed at the same time. And for that reason, I have invited Xiaochen Liu. Welcome, because that's exactly a topic that you're researching.
Yes, thanks. Welcome. My research focuses on the design of the optical receiver. My goal is to make the receiver faster and capture more stronger signal, and eventually achieve a higher throughput.
And can we show exactly what the photodiode is, what it looks like, and what it does? So we have a device that captures photons.
Yes.
Is it as simple as that?
Yeah, so we call it photodiodes. So the function for photodiode is it captures a light flux and then converts it into electrical current.
Basically, photon comes in, electron comes out.
Exactly, yes. And as you can see on the left side of the screen, this is what usually a photodiode looks like. And on the right side, it is an equivalent circuit showing what is the electrical function or characteristics of the photodiodes. Mm-hmm. You see on the left side, there's ideal photocurrent representing the photocurrent that's generated by the photodiodes. And then you can see the parasitic capacitance, resistance, serial parallel. And most importantly, you see in the middle, there's capacitance over there.
Most important, but I would not like it, as a capacitance is ruining high-speed communication. Very fast fluctuations of the current just all go through that capacitor and are absorbed by it. So it spoils the game.
Yes, that's let's say that's a challenge that we're facing.
So I cannot just order a photodiode with zero capacitance and then I have the nicest communication system.
Well, ideal world, everybody wanted, but practically it's not possible. So if we have a photodiode, the capacitance is like a package deal, so it comes with the photodiodes.
It's basically the area, the size of the diode, in which we can store, in which the device will store electrons and holes, and that is exactly a capacitance. Yes. So it is inherent to it. What can we do? How do we amplify these signals? What do people typically do when they take a signal out of the photodiode?
So now I'm showing two sketches of how we process the photocurrent after it's received by the photodiodes. Mm-hmm. So this first one on the left side is this photodiodes with impedance matching amplifier. So basically it's just really simple. It's just get the signal and then amplify by this operational amplifier.
And that sounds like that is what you should do.
Yes.
As in the impedance matching theorem, it says that you get the highest amount of power out of a photodiode or out of a source by basically matching the impedance. Yeah. But in a receiver, it's not about the highest power. It is about the best signal to noise ratio and to extract a good signal in a noiseless environment.
Yes. So let's say at this time, this impedance matching amplifier, let's say the frequency response all follows characteristics of these photodiodes. But let's say to achieve a high signal to noise ratio, we use this right side scheme, which is connect these photodiodes to a Trans-Impedance amplifier. At this time, the frequency response, as you can see with the white curve, is flattened by this amplifier.
So the design of the Trans-Impedance amplifier is made in such a way that the frequency transfer function is flat by some special tricks with the amplifier. But the disadvantage is that the noise is no longer flat.
Yes, as is shown in the figure on the right side, this red curves. So you can see the noise is amplified at high frequency, or is boosted.
Yeah, now I would say we take the design on the right side or on the left side, but in the end, all that matters is that the signal quality, the ratio between the signal strength and the noise level, worsens if we go to higher frequencies. And that's inherent to using a photodiode in a wireless communication system using light.
Yes, and we at this time we can use the term to basically analyze this common influence of the gain and this noise. We call it gain to noise ratio. Basically, we take the ratio of this gain, which is the Y curve, and over the noise, which is the red curve. Basically for an optical receiver, usually we see that this gain to noise ratio have this low pass characteristics.
Okay. And then what I'm reading in a lot of scientific papers is that there is a trade-off in the design of the photodiode. On one hand, you want to make it big, you get a lot of photons, you get a strong signal, and you want to make it small because that gives a small capacitance and therefore a high bandwidth. It is a trade-off. Few or none of the papers that I know really quantify that, and I invited you because you try to quantify it. If people say there is a trade-off, there should be an optimum, and you try to reach that optimum.
Yes. We can show some result, but this, let's say, this is for something for later, but this optimum really depends on the strategy that you're using to process a signal.
Okay.
So maybe we can start with, let's say, the simplest strategy, where when we modulate the signal, we only use the flat spectrum of this gain to noise ratio. So
it sounds conservative because you're not going beyond that 3 dB bandwidth. You're not using that, but it is safe and it may be easy to design in this.
Exactly. This is the let's say the safest approach. Let's say we have this sketch on the right side figure, but the conclusion we get or the result we get is that the size of the photodiodes actually matters. And how that matters, we can show you in the figure. So I'm showing this result with...
There's an interesting curve, and I do see a maximum.
Exactly.
So there is an optimum.
Yes.
We confirm that, and you show where it is. But maybe we first look into the shape of the curve. Huh?
Yeah.
Assume that I'm far away from the transmitter, therefore my signal will be weak. Yeah. And I can imagine that all I want to do is basically capture photons.
Yes. At this time, you won't need a big detector size as big as possible. That's what we see the increase from a small detector size, it goes up, and then the throughput goes always up with it.
Yeah, and the slope can easily be calculated simply because doubling the size gives you twice as many photons, gives you twice as much current.
Yes.
4 times the power, so that's a bit more the complication in the analysis. All right, but that goes up to some maximum.
Yes.
And then the curve starts to decline again.
Yeah. And at this time, the system is, let's say, the bottleneck of the system is no longer the signal strength, but the bandwidth we're using. As we say, we only use bandwidth that is flat, and this flat spectrum is related with, let's say, the size of effective area of this of this photodiodes. Mm-hmm. So as we increase the size of the photodiodes, you are allowed to use smaller and smaller bandwidth. And with a small bandwidth, you can achieve less smaller throughput.
So if you have a lot of photons, very strong signals, it's better to go for a smaller photodiode. And I think I can relate that to some of the Shannon equations. And everyone warns me, you should not use the Shannon equations on optical communication for this purpose. But nonetheless, in a later paper, even Shannon showed that what is generically always the case is that if you want to have more power, you need to have exponentially more power if you want to boost the bitrate, because you need many, many levels. And levels is the exponential in the number of bits that you want to transmit. And it's linear in the bandwidth that we have. So bandwidth is more important if the signal is good. And that's why there is really this optimum.
Yes.
And...
Actually, you can calculate this optimum based on how much power you have, what kind of detector you have. So this optimum can be calculated or can be quantified.
And you, Xiaochen, you found a way to calculate that and do the derivation for it.
Yes.
But from there on, we can still improve, because only conservatively using the bandwidth in which the signal transfer is flat, of course, is not the optimum to do.
Obviously, yes. Or according to whatever we have done, yes,
we can do better.
We can do better, yes. And that's what I'm going to show. So how can we do better? So previously we used a, let's say, conservative approach where we only use a flat spectrum. But what we can also do is we go beyond this, let's say, comfort zone. So we go beyond this flat spectrum and we use a higher bandwidth, but we do something later.
Mm-hmm. If we go beyond that 3 dB bandwidth, Then with the Trans-Impedance Amplifier, we flatten the response, so that would not immediately be a problem. The response, we don't get the inter-symbol interference with the low-pass filtering, but the noise goes up. So we pay a price in having a lot more noise if we go too far in extending the bandwidth.
Exactly.
All right. And how do you choose the bandwidth then?
This bandwidth is also object for optimization. It needs some mathematical stuff, which is not shown here. But
for that, people have to read the paper.
Exactly.
But it may be interesting to see what your conclusion is.
Yes.
Okay. So I guess it is better.
It is better, and it is should be shown in this figure.
Mm-hmm.
So you may remember the solid line from the previous slides, where we use a flat spectrum, where you can see a optimum. But if we go beyond this, flat spectrum, and we use whatever we're trying to optimize, we see that the size of this photodiodes doesn't really matter anymore. So we didn't see it. There's an optimum, but we see
it flattens. It goes up in the same way as it used to be, because you want to have more photons when the signal is weak. But then when you have enough, then basically you should not shrink the photodiode because it doesn't help anymore. And what's happening there then? Nothing, basically, because the curve is flat.
Yeah.
But apparently you get more signal, there is more noise, but you get enough more signal to compensate for the noise problems that you have.
Yes. Basically, at this time, you're really going far away with, you're really using a lot of bandwidth. Come again, this is really like a theoretical result, and other things in real world may happen. Maybe the limitation of the amplifier, also the limit, or the parasitic capacitance or impedance in the photodiodes, it can have effect to the result.
So basically, don't stretch that to very, very high frequencies, because at that moment the model fails. But as long as we can just model it as a capacitance and a current and an amplifier that is doing quite well, then this curve holds.
Yeah, if we put it in a safe way to phrase it, we can say that the size of the photodiodes does not matter that much if we try to extend the bandwidth that we're using.
And I would think that a designer may like this, because if we put the photodiode on a smartphone and you have to decide how large to make that photodiode, you do not know how strong the signal is. You may be very close to the transmitter, you may be far away. So it has to work under multiple conditions. And basically, the curve says, make it big enough.
Yeah, you can try to do that. Yeah.
And but it also says that the trade-off is not so much a trade-off, but a kind of, you need a minimum size.
Yes.
All right. This was trying to be a bit smarter. We now use a modulation method that spreads its power in a uniform way up to a certain frequency.
Yes.
But there are smarter modulation methods. So is this still the best we can do?
This is not yet the best we can do. We also have... because now we have the information of the gain to noise ratio over the whole spectrum, and which means we can actually do something on the frequency domain. And now we can introduce this OFDM, where you can basically play with every frequency being. Basically, first you do a Fourier transfer to the frequency domain, and you can play with how much power you allocated to each frequency being.
Yeah, OFDM, orthogonal frequency division multiplexing, means that you put multiple bits on different frequency bins, and you can play with all these frequency bins. You can allocate different power to different frequencies, more bits to the lower frequencies, and really optimize on how you do it. But that optimization requires Lagrangian optimizations, a lot of math.
Yes, and let's say that one way we play with how we allocate this power to each frequency being, we call it water feeding. Basically, we have a bottle of power of water. We pour this into the gain to noise ratio. So the gain to noise ratio just have a higher potential. It gets more power or gets more water. The gain to noise ratio is a frequency being with lower potential. It gets lower power.
Yeah, you try to explain it in a very visual way. The first result by Bob Gallagher, I think, was a relatively mathematical result.
Yes.
And he gave a beautiful interpretation of that, which is basically take the transfer function and find an easy graphical way of allocating the power. That's what you did.
Yes.
And you get better results.
Yes, we can see what the result looks like. And so actually the solid line represents water fading. You see that with the increase of the photodiodes, the OFDM with water filling has the potential or actually surpass the signal processing scheme where we only play in a time domain, POM or something.
So it is a bit better.
It is better, but there's also shortcomings because OFDM it do need a higher DC power to compensate let's say the high PAPR after the Fourier transfer.
So you pay a bit of a penalty there.
Yes.
I read quite often that OFDM is spectrally efficient. I doubt that because OFDM is nothing else as doing a rotation of where you put your bits in the time frequency domain. The number of symbols per second per hertz remains exactly the same with OFDM.
Yeah.
So there's no gain in this respect. And I like to debate that with people who challenge it, but okay, for me it's not the case. The reason for using OFDM is that you, in a very surgical way, can precisely give the right amount of power and the right number of bits on each and every frequency. And that improves the throughput, improves the performance, and really makes sense for these kind of applications.
Yes, exactly.
If we talk to the modulation experts, to the signal processing experts, we get this. We know how to optimize the bandwidth and the modulation methods. Yeah. Can I also go to the optics guys and say, why don't I put a lens in front of the photodiode and I just focus all my photons on a very tiny spot?
Yes. So this will be another approach of the receiver design, where we call it an imaging system. Basically, the simplest idea is we put an optical lens to first gather all the lights into this lens, and then the lens focus all the lights into this small point, where this small point can be captured by small photodiodes. At this time, you use a small photodiode, so have high bandwidth, and then you also get all the signal. So
that would be a great approach, and it works very well if you know where the laser beam is coming from, because then you can rotate the lens and design the whole system.
Yes.
That is being used for free space optics, for communication links over larger distances where you can rotate a lens, but I wouldn't know how to integrate that into a smartphone. So to have a kind of small detector and just have the communication from any angle anywhere in the ceiling, then you need to know how to decide on the size of the photodiode. And that is something that you have been quantifying, particularly for these mass market applications where you want to make it small and where you even want to get it in the smartphone.
Yes.
Now, I guess scientifically that's an interesting result.
Yes.
Because you quantified exactly how this trade-off should be made.
Yes.
What should we ask our viewers to do? To subscribe to the channel? That's not the way it works in science.
Or even better, please, if you're interested, please check our publications. And if you're also doing similar research in the same area, and please refer to our papers and cite our paper if you want.
Yeah, and preferably there is a trade-off of high bandwidth versus strong signal in a photodiode. Yeah. But as Xiaochen Liu quantified, we know that there is an optimum or there is even a minimum size, depending on the application.
Exactly. Yeah.
And that's, I think, a very interesting result that we would like to share, and that we also like to get comments on, and of course that we like to be cited in literature.
Yes.